Hey guys, as promised, these are going to be the proofs for the other four trig derivatives. I have them paired up. The derivative of tangent x, the proof is almost identical to the proof for cotangent x, and then secant and cosecant, same thing. So, due to time constraints, I just kind of told you the derivative of tangent x is secant squared x. The derivative of cotangent x is negative cosecant squared x. But why, you may have asked, and that is our job for today. It comes down to quotient rule and then a couple of basic trig identities. So before we apply the quotient rule, we need to turn these into quotients. So what I'm going to do for tangent x, before I take any derivatives, so that derivative notation is still there, I'm going to rewrite tangent x as sine x over cosine x. Those are the same thing. That's technically a trig identity, but it's just kind of a fact. And so now that we've written tangent x as a quotient, we can differentiate using the quotient rule. So it's going to be a little bit ugly to look at to start with, but then we'll see it turns out quite nice. So we know it's a low d high minus high d low, all over low low. So I'm going to go ahead and put my subtraction up over there. So low, d high, minus high, d low, all over low. And so let's go for it. Low is cosine x. D high means the derivative of the top. The derivative of sine x is also cosine x. That's a derivative. So that's low d high minus high sine x d low. The derivative of the denominator, derivative of cosine x, is negative sine x. That's another derivative there. Low d high minus high d low, all over low low. And that doesn't look anything like secant squared of x, but it doesn't take much to get it. So we'll just start simplifying. I have cosine x times cosine x. So that's cosine of x all squared, or cosine squared x. And then over here, I'm subtracting sine x times negative sine x. Negative times a negative is positive. Sine x times sine x is sine squared x. That looks familiar. And all of that is over cosine of x all squared, which I'll write as cosine squared x. Okay, so all that happened there was simplifying that numerator, getting the parentheses to go away. And that still doesn't look like secant squared x, but it's about to. One of the most important trig identities is the trig identity that tells me cosine squared of theta plus sine squared of theta equals 1. Sine squared plus cosine squared equals 1. And so if I use that fact, then that crazy numerator is actually just the number 1. Again, that's a trig identity. Cosine squared of any angle, whether you call it x or theta or Steve. Cosine squared of the angle plus sine squared of the angle equals 1. It's, again, one of the most important trig identities. And so now it looks a little bit better. 1 over cosine squared of x. The reciprocal of cosine squared of x is secant squared of x. We have proven through that process, we've proven that the derivative of tangent x starts off looking really gross because of the quotient rule, but then after some trig identities, turns out being real nice, secant squared x. For cotangent x, the proof is nearly identical. So to save you the horrible experience of watching me go through it again, I'm going to pause the recording and just kind of do it. And so in just a moment, it shall appear. I'll be right back. And I'm back. And there it is. So over on the right-hand side, same general process. Of course, cotangent x, turns into cosine x over sine x. We applied the quotient rule, so you can see your d high, so low d high minus high d low. So those are still there. And so what we've ended up with, in contrast to the previous, is our numerator is negative sine squared x minus cosine squared x. And that's the same as this identity, just with everything multiplied by -1. So that numerator is -1, and my denominator is sine squared. That's how we end up with a negative cosecant squared x, as opposed to a positive secant squared x. We did on the left. I'm going to do a different video for secant x and cosecant x derivatives, but this basic idea of just rewriting it as a quotient, then applying the quotient rule, and then using some trig identities is going to apply to those proofs as well. See you there.